Now we're going to discuss the cosmic microwave background. What is it? How do we learn about it? And what does it tell us about the universe? So as a reminder, the Hubble Constant measures how quickly galaxies are moving away from us. And if we look at the pictures, we saw that in the past, galaxies were closer together. We see now galaxies are moving away. And so if you just play that movie in reverse, instead of the universe going away from us, it's all collapsing in. And so that inverse of Hubble gives us the Hubble time when all the galaxies were compact, dense, and on top of each other. And we get an estimate of the universe being about 13.7 billion years old. Here's that picture in reverse again, right? Here we are today. The galaxies are further and further away from us, expanding and expanding. But you run that tape backwards, you run the video backwards, and you'll see that things are getting closer and closer, compressing down to the singularity. These observations made by Hubble were the first predictions of this concept of the Big Bang. People had philosophized about this idea of the birth of the universe, but this was the first hard evidence that such a thing existed and is scientific. So, 13.7 billion years ago is what we consider the Big Bang, when the universe burst forth from a singularity. Think of how we describe black holes. We say the black hole is all that mass concentrated into a single point in space-time. Right? Same thing, but instead of being just a lot of matter, this singularity was everything. I do mean everything. All the matter and all the energy of the universe. All that was in the singularity, and when it finally burst forth, for whatever reasons that it did, the universe started expanding. And think back to the rubber band analogy in the last part. Everyone is exploding outwards. Literal space-time itself is what is expanding outwards, getting bigger. So, one term we use to quantify this rate of expansion is what's called this scale factor, labeled a R subscript U. Right? Basically, the smaller the scale factor, the smaller the universe is. And definition, we say this is 1 over 1, or 1 divided by 1 plus this redshift parameter. If you do the algebra, bring back the definition of this galactic redshift parameter, you'll find that it's actually just the straight up ratio of the rest wavelength, what we expect, over the observed wavelength that we measure. Remember, the universe is always getting larger and larger. It's always expanding outwards. So the observed wavelength is always going to be this longer, more stretched out value. One way to think of this, we're going to upgrade from my rubber band analogy to this like rubber sheet that we have here. So as the rubber sheet gets bigger, right, not only am I stretching one way, I'm stretching both ways. So I'm doing a expansion this direction and this direction. Let me say, look at a square here. There's my one square. Let's try that again. Here is my one square I'm looking at. That represents, say, the galaxy, right? Now let the expansion continue, and that same guy is now bigger, right? So this scale factor RU is basically measuring how much bigger this guy is compared to the smaller one. That's what the scale factor is saying. So what we've been saying before is that we look at the red shifts of these galaxies and we call this Doppler effect. We say, hey, those things are moving away from us. Since they have some inherent speed, there is this Doppler shift associated with it. But to be precise, what's actually happening is that this isn't a Doppler shift per se. The literal fabric of the universe is what's stretched out. Imagine that I've got a sound tube between us. I have this tube that I'm speaking into. And all of a sudden, as I talk into the tube, someone grabs the tube and just starts stretching that material out. And that becomes an elongated wave because the wave's still in the tube. The wave's still there. And all that's happening is that the distance it's traveled has been stretched, wrung out. And so the redshift that we observe in the galaxies, it's not to say specifically that the galaxies are moving away. It's the literal fabric of reality is getting bigger and shifting that material away from us. So what does this have to do with this cosmic microwave background? What are we getting at? Well, remember, when the Big Bang happened, there was a lot of energy out there. And there's still radiation from the Big Bang. That stuff would have been very hot and very prevalent throughout the cosmos. Now, as the universe has expanded, those thermal photons produced at the birth of the universe, they're still going to be around. They're still going to be prevalent. And the universe is now stretching and taking those photons that were nice and hot and cooling them down because they're getting redshifted because of the galactic expansions. So, what we want to do is find this light from the early universe, find those photons. There's a bit of a hiccup that we have to go through. Where are these photons? Why can't we see them yet? If I look at the very early universe, this would be this region. You've got the Big Bang has happened, and now in the microseconds, the seconds after that, where I just have this gigantic soup of some protons, some helium, mostly protons, electrons, and a lot of energy, a lot of thermal energy and photons. These photons are bouncing all over the place, but they're kind of trapped. Basically, what's happening is that matter is ionized. Right? Go back to my proton, electron orbiting it. If these things are too hot, well, the proton can no longer hold on to that electron, so the electron just flies off. So everything is charged material, and charged material definitely produces more and more photons, and more readily interacts with photons. So in the early universe, it's just too dang hot. Right? Photons are scattering off electrons, hitting protons, bouncing over. There's no way for them to travel freely. Then, eventually, the universe starts to cool down, and you reach what's called the era of recombination. Effectively, temperatures have finally cooled off now that protons and electrons can finally bond again. They can finally recombine and start forming stable, neutral atoms. And when that happened, finally, the earliest photons in the universe could expand outwards and be there for us to detect. So the photons from the beginning of the universe are still with us today. They stem from about 400 years after the Big Bangs. That's when error recombination finally occurred. The visual analogy of what recombination is you have a hazy universe. Electrons and protons are separated from each other, and the light just bounces and scatters, absorbs, reabsorbs. It's like looking at a very foggy day. After recombination happened, finally, the electrons and protons have become these nice neutral objects, and now these photons are free to escape and travel the cosmos. The analogy, it's as if we've lifted the fog off of the universe. And finally, those earliest photons are allowed to just propagate freely and for us to observe them. So to recount, the photons from the Big Bang would have to have been very hot. And then you account for the expansion of the universe. And you'll find that by now, through just galactic redshift, the expanding of universe, those photons should now be around 3 Kelvin in temperature, much cooler, much shorter wavelengths. But the distribution pattern should reflect something like a black body radiation, where there is a peak temperature, but a full spectrum, a full range of frequencies or wavelengths being emitted. So these are the two gentlemen who are lucky enough to find this cosmic microwave background. That is Arno Pinzius and Robert Wilson with their Horn telescope. Absolutely great story. These guys did not set out to detect the cosmic microwave background, the earliest photons of the universe. They were just playing around with some old equipment that company had given to them to do some experiments with. And they had an issue where no matter where they aimed the telescope, there was this constant buzz coming in, this constant hiss. And so they moved their telescope, re-aim, and once again, the same hiss. And it was interfering with the work they were trying to do. And they became obsessed with trying to solve this. I kid you not, to some accounts, they literally were on their hands and knees inside this telescope, scooping and scraping pigeon poop out of their telescope. They were so convinced that pigeons pooping in their telescope was interfering with their work. And even after going to that level extreme, still finding this strange hiss constantly no matter where they aim their telescope, they finally started throwing their hands up in the air and contacting other physicists going, what gives? And when they finally reached a theoretical physicist who was able to tell them, oh my goodness, you guys discovered the stuff that we've been talking about for decades. You guys just accidentally found it. They both were awarded a Nobel Prize, and both of them acknowledged that they felt like they were the dumbest people to ever get a Nobel Prize because they were not looking for the cosmic microwave background. They just inadvertently discovered it. So with that history to the side now, what they found is this radiation from the beginning of the universe. And the emphasis, it comes from all directions around us. Remember that statement earlier about how everyone has equal claim to being the center of the universe. These photons are propagating equally in all directions. So here's one of the first images of the CMB, the cosmic microwave background. This is taken by the Wmap Satellite. And you notice that there is variations, fluctuations across this thing. And these images are very blurred, right? So we want to get the best, highest resolution image of this picture as possible, of these photons. They're in the microwave range now because of the galactic redshift. But the better we understand this picture, the better we have a map of what the early universe looks like and how that projects into the galaxies we see today. So improving upon that, upon our CMB measurements comes the Wmap Satellite, and you get these high resolution pictures where you see the hottest of hot spots and the coldest of cold. And this image gives you this idea of this huge, wide range of temperatures across the early cosmos. But in fact, this part here, the hottest, versus the coolest, they are only 1 in 100,000th difference in temperature. So even across this entire picture, there's only this minute variation across the entirety of the cosmos. Should remind you of that homogeneity that we've discussed before. The universe is very homogeneous, and that reflects all the way back to the beginning of the universe. And any small fluctuations that we see here, well, that corresponds to dark matter clumps that we saw in our previous sections of how galaxies started to form together. The little fluctuations in here corresponds to little fluctuations in density that ultimately led to the formation of galaxies. So here's a collection of all the different maps that we've tried to stitch together of this cosmic microwave background. Understanding this picture, getting the highest resolution of these photons, gives us the best data of what the early universe looks like and helps us model how we got from that universe from billions of years ago to where we're at today. So as a reminder, a test of your memory, this grainy distribution, how big is that fluctuation? Percentage-wise, from the hottest to the coolest regions, remember, 0.001%. It is only a tiny, tiny fluctuation throughout the cosmos.